Hello, in this video I'll be explaining the implementation for uh, the initial set of tasks that were given as a part of the GSOC problem statement by Pal Robotics called visualization, payload and metrics. So here I have my package called Robot Pinocchio, and I have an initial set of proof of concept file uh, try RBD, and this is the node where I've implemented the initial set of tasks that are supposed to be performed. If I have to give a rough architecture, we've implemented a class here which sort of it creates it subscribes to the robot description topic as mentioned in the problem statement, and it initializes some set of variables. In the end, the node creates a callback to a timer, um, sort of internal timer. Now here we will have two callbacks, one for subscribing to the robot description topic and one for the timer that has been created. Now the reason I've chosen this sort of architecture is because we do not want that the same function has the functionality to extract data from the robot description topic as well as to calculate the rest of the stuff as well, because um, ideally we would want ideally the robot description topics is only going to publish it publish the URDF once, and so the callback is supposed to be called only once, whereas the timer callback is supposed to be called multiple times for reasons that we'll see soon. So here, if I'll just I have the functionality implemented down, and I'll just walk you through uncommenting and just running it. Before that, I'll get the simulation started. Now the Tiago robot library is the one that we'll be using for the sample simulation, and for any sort of robot library, the bring up package usually has the scripts to sort of just a second. Uh, Sorry, the description package has like the sort of basic architecture to launch RViz, to launch Gazebo, and what all for simulation. Now here we have two launch files. One is robot state publisher and the other one is show. So the show launch file also calls the robot publisher launch file, but it additionally adds stuff like RViz where we'll be able to see. So this is the launch file that we'll be launching. So I'll just quickly uh, open a terminal here, and we can start looking at this. So here I'll be first launching this. So ROS to launch, and this workspace is already sourced. I did not source it right now. And the name of this particular package is Tiago description. So Tiago description, and the name of the launch file is show. So show.launch.py, and this is launch the robot in RViz. So here we can see that we have the robot with this end effector, and currently all the transforms are being published and the entire chain is set up. Now the robot state publisher node is publishing the URDF on the robot description topic. So now what we're going to do is we're going to start running our node. So for the initial set that is given here, so we'll just go task wise. So the first task was to get the data and extract the robot model, and that is what this function does as well. It extracts the string from the data that has come in the message, and then uses the build model from XML format to develop the model. And here we can see that we'll get the sort of output when we're going to run this code right now. So I'll just comment the rest of the things that are here and show the implementation for the first task. So just we'll go to the workspace. So this is Colcon workspace. We'll have to do Colcon build since we have modified the file. Maybe we're just going to run ROS to run. Name of the package is Robot Pinocchio, and the name of the node is try RBD. So, and let's have a look at the information that's published here. So we've successfully retrieved the robot with the name Tiago. It has also found 30 geometric objects, and right now, since the timer callback just generates a random configuration and calculates forward kinematics. The configuration is being printed for that particular thing. Moving on to the next task is to get transformations. Again, it's been implemented in this function. So these functions just sort of act as a layer to mask the internal sort of part that is supposed to be there here. So we can get transformations directly as OMI from the data.zip of the model itself, but we have written a function here so that we'll actually be able to log it and visualize it as well. The initial part of the function just gets a random configuration. It identifies the number of joints that are there in the model from the one that we have generated earlier, and it generates random n-dimensional configuration space values between minus pi to pi. So, and it calculates the forward kinematics and Jacobians. So the function has forward kinematics, it updates the frame placements, calculates joint Jacobians, and then updates that again. So we'll run this again. We'll build. And now we can see that for a given so for the given configuration that we have used, the node has published just a second, so I think this is running way too fast. I'll run it once and then stop it. Yeah. So initially it has taken some random configuration, and for that particular configuration for each of the joints it has published the homogeneous matrix, that is the 4x4 matrix for that particular joint, and that is being done for all the joints. Since this is in the timer loop, every 1 second a random new configuration is generated and the transform for that is published. Now it is important that we call this before we actually log the transforms, because generating a configuration is just getting a variable, but then actually calculating the forward kinematics updates the model and the positions that each of the links has. So yeah, that is a bit important here. The next task is to get the frame Jacobian for the end effectors. I've identified the end effector ID, the end effector ID to be 87, that is the 87th frame in the structure, and this is just going to print the Jacobian of the arm tool frame, Jacobian of the end effector frame, data for the end effector, and we can just comment right for logging transforms right now. We'll go for Kulkan build and run it again, and I'll just cut it here so that we'll be able to have a look at the result. Again, it has used a random configuration. It has found out what the frame for the end effector is, that is the rotation matrix of the end effector frame and the position of the end effector frame with respect to origin. Then it has also printed the Jacobian for the end effector matrix. So this is a joint Jacobian, and similarly Jacobian for the arm tool frame as well. So the frame Jacobians for both the frames have been printed here, and then the next one is just it looping again. So just comment this again. The next part was task 4, which is adding collision pairs. So I'll just uncomment that part. Yes. So here basically firstly we are adding all the collision pairs. We are finding out how many collision pairs do exist. Collision pairs can be collision pairs between links of the same robot, or a robot and another robot, or a robot and some collision object that's been added to the environment. And once we have added that and identified the collision pairs, we just compute collisions, and it provides us the data of the collision, so we can log number of collisions and the information regarding that. So just quickly run this so that we'll have a better idea by seeing the output. Yes. I'll just cut it here. Now what this has done is, for this particular configuration, it has identified 371 collision pairs, and of the 371 pairs it goes towards every pair and finds out if there has been a collision or not. And here we have found out that there are total 38 number of pairs which are colliding with each other, and it has printed the collision pairs for which the collision has taken place. Now the important part, and for the first collision pair it always prints if there has been a collision or not. Now the important part is that these links here might just be that the URDF file itself is placed in such a way that the parts collide with each other. So it is going to be as simple as just saving the pairs for which collisions are to be ignored, and we can just remove those sort of collision pairs from a standard function from the Pinocchio library itself, and with that we now have the collision checking functionality as well. So ideally we would want that any sort of issues with the URDF that is causing it to portray a self collision, we are able to remove that before calculating it, so that any other forms of collision we just, if even if one of the collisions is true, then the robot is in collision, and that will be used later on in the project. I'll quickly comment the part for task 4, and finally coming to the final task, that is for payload calculation. So again, logging is already implemented. I'll just run the code and I'll show. Okay, I'm sorry. Um, okay. Yeah, anyway, so the first function is to calculate the maximum payload for a given configuration, and here we can see that for this given configuration the maximum payload that it has calculated is 86.46, and hence for a given configuration we are able to find out the maximum amount of payload that that particular robot in that particular configuration can take. Additionally, after that we have the talks that are required for producing this particular configuration, and that is just being printed here, that for the various joint IDs what amount of torque is being used and what is the sort of maximum torque that is placed here, that the limit sort of allows. So here we can see that this is the one where it is sort of on the edge, and that is why the algorithm has broken out of the loop here. So joint with ID 6 is the one which will reach its limit first, and it will reach it at this particular payload. So with this we not only have information about maximum payload that it can take, but the subsequent functions also sort of allow that given a particular payload it calculates the amount of torque ignoring the effort limits that have been put in here. So yeah, that has been the implementation of the functionality for the part that has been given so far. Yeah. Thank you.